Another example of Newton's laws being applied to solve a problem on an inclined plane reads as follows. Calculate the angle of the incline on which a 7-kilogram object accelerates down the incline at 5 meters per second and against an applied force up and parallel to the slope of 5 newtons and a frictional force of 2 newtons. And so we always start a question like this by drawing a free body diagram for ourselves, where we can see that there's a force of gravity that acts vertically downward on this object. There is a frictional force that acts up the slope parallel to motion, and there's also an applied force of 5 newtons that acts up the slope. Because this object is on a surface, we know that there will be a normal force acting perpendicular to the surface. We would normally start a question like this by resolving our force of gravity into its two perpendicular components, where we are reminded that the force of gravity can be resolved into two components called Fg perpendicular, the component of gravity that is perpendicular to the slope, and Fg parallel, the component of gravity that is parallel to the slope. And we can determine that by creating a triangle here where this angle theta is the same as the angle theta of the incline, and these two are perpendicular to each other. So we can then write an expression that says that Fg perpendicular is equal to Fg cos theta, because that is the adjacent side of the triangle, where the force of gravity is calculated as the mass of this object, 7 kilograms, multiplied by gravitational acceleration of 9.8, so 68.6, multiplied by cos of theta, where theta is unknown at the moment. We can then also calculate our perpendicular component of gravity, the parallel component of gravity, that being Fg sine theta, because it is the opposite side of this triangle, where Fg is once again 68.6 and sine of the unknown angle theta. Normally we would have the angle of the slope and we'd be able to resolve that into a force. In this case, we can't do that, so we leave those expressions as they are for now. What we can now do, though, is we can say that since this object is accelerating down the slope, there must be a net force acting on it by Newton's second law, and that net force is calculated by taking the parallel component of gravity, that is the only force that is pulling this object down the slope, and seeing that there are two forces that are pulling this object up the slope, those being friction and the applied force. So we can calculate our net force by saying that that is Fg parallel minus the applied force minus the frictional force, again equal to the mass of this object multiplied by its acceleration, where we can now say Fg parallel, we don't know the exact value, but we have the expression for it, 68.6 multiplied by sine of theta minus the applied force given to us as 5 newtons and minus the frictional force also given as 2 newtons multiplied, or is equal to the mass of this object, 7, multiplied by its acceleration of 5. This can be rearranged for us to find that sine of theta is then equal to 42 over 68.6, and then we can use the calculator and the second function of sine to find that theta is equal to the second function of sine of 42 over 68.6, which tells us that theta is equal to 37.75 degrees. So to recap, we have shown that it is possible to use Newton's second law to determine the angle of an incline. This is possible because we can write an expression with that unknown angle theta for each of the unknown forces, and then solve using the information that we have for that unknown angle.